Greetings everyone, and welcome to another pre-lab. Last unit we examined uniformly accelerated motion. We looked at all the different ways we could represent it, with position, velocity, and acceleration versus time graphs, with motion maps, with a set of 4 wonderful kinematic equations. And now in this unit what we're going to do is to look at why do things move with uniformly accelerated motion. So we're going to kind of follow the pattern that we did at the beginning of the year when we examined constant velocity and then why things moved at constant velocity. And we found that things moved at constant velocity because the forces acting on them were balanced. Right? The forces, the net force, if you will, had to be 0. The forces had to cancel. So in this lab, we want to look at why do things accelerate the way they do. And so we need to know what variables affect the acceleration of an object. Now we already know one of those variables. We know from Newton's first law that in order for something to accelerate, those forces that we mentioned a moment ago have to be unbalanced. In other words, there must exist a net force on the object. And the size of that net force is going to affect how quickly something will accelerate. Remember, that's how quickly it will change its velocity. Well, there's another variable that will be factored in here. If I took the same force and pushed on some big 200-pound student and then took that force and pushed on some 100-pound student, would the acceleration be the same? Of course not. Right? So the mass that the force is being applied to will affect the amount of acceleration that results. Now, this is kind of a cool thing because it's our first 3-variable lab that we're going to do this year. And all of our other labs have always been just 1 variable compared to another. Now we're going to have 3 variables. It's going to take the lab a little longer and a little more complex for us to deal with it, because we have to be able to control 2 of those variables and measure the third. So we're going to use a kind of a complex lab setup here. We're going to use a modified Atwoods machine. Now, we've talked about those a bit before, but now you're actually going to get to see one in use. A modified Atwoods machine consists of a cart on a track, very, very low friction carts, attached to a string which runs over a massless, frictionless pulley, which is not really that far off from what we have to use, as you'll see when you get back there. And then that string runs over that pulley to a mast that hangs off the side. When you let everything go, everything moves and it accelerates. This device is going to allow us to control some of the things. So let's talk about the variables with respect to the modified Atwoods machine. First of all, the mass. Now this is the mass that is being accelerated by the net force. So if you think about the modified Atwoods machine, what's being accelerated? Well, the cart's definitely being accelerated, but not just the cart. The hanging mass is also being accelerated. So when we're talking about mass here, we're really talking about the total amount of mass. The mass of the hanging cart the mass of the cart on the track and the hanging mass. This would be what we would call the system mass. So we're going to look at this modified Atwoods machine, as we did in previous units, as a system and call the mass the entire amount of mass. The cart, anything we put in the cart, and everything we have hanging off the side. Now for our next step, let's take a look at the forces that are acting on this modified Atwoods machine. And as we just discussed, we want to look at it as a system. So this might look familiar to you from a couple of units ago. Here is the system diagram. We have the cart, we have the hanging mass, and notice the way that the hanging mass is oriented. Essentially, I've taken the pulley and the string out of here so that we don't have to worry about it. I've taken this mass and slid it up next to mass A, next to the cart. So, what forces act on the system? Well, of course, it interacts with the Earth, and there is a force of gravity. There is a force of gravity which pulls down on cart A. And notice I'm using an extra little subscript so we know which force of gravity we have. But there's also a force of gravity acting on B. Now, in real life, that would pull down on B, right? And it would make everything accelerate. But since we've pulled B up next to A, since we're trying to get rid of the pulley, you can see by the way it's oriented, that force of gravity would act horizontally. In other words, this is the force of gravity that's pulling the entire system. Okay? Now, the cart is also supported by the track, and so there would be a normal force acting perpendicular or up. That normal force would, of course, balance out the force of gravity. A. Right? So these two forces would have to cancel. How do we know that? Because the velocity does not change on A vertically. A is only moving horizontally. It's accelerating horizontally, but not vertically. And that's a new way, by the way, that we can start to express Newton's first law. If something has balanced forces, then it doesn't have an acceleration. Right? So it's not accelerating this way. Now, there could be a couple of other forces depending on how we have this set up. Right? There could be friction, and there could be an angle to the track. Well, I didn't want these two variables in here. I didn't want to make a 5-variable lab. So when you get back there, you'll notice that I've done something. I've put some leveling feet on the track, which is a little bit different than when we've used them before. And now, when you give the cart a little push, it will move at constant velocity down the track. And the only way that'll work is if the track is tilted so that friction and angle of the track all kind of cancel out. In other words, by tilting the track slightly, I'm making it act like it's perfectly frictionless and there's no angle. So it looks like in the diagram and it's frictionless. In other words, we can neglect those forces. So that's kind of one little thing I've done with the setup. Okay, so again, when you get back there and you pile all the masses on, give your cart a little push and see if it moves with constant velocity, and it should pretty close, which means that those forces aren't really being involved here. Okay? That way we can just focus on these forces that we have here. That means that the net force is the unbalanced force of gravity acting on the hanging mass, F of GB. And we did a whole lab on this. We know how to calculate the force of gravity acting on B. That's equal to the mass of B times the gravitational field strength, which we know near the surface of the Earth is 9.8 newtons per kilogram. So in other words, we can figure out how much net force we have acting by figuring out how much B weighs, the force of gravity acting on B, which is just the mass times gravitational field strength. That means that we can control how much total mass we have, and we can control what the net force is. So those will both be independent variables, that's I for independent, and our acceleration will be our dependent variable. So we have a lab here with 2 independent variables we can control and 1 dependent variable that we will measure. So the purpose of this lab is to create graphical and mathematical representations of the relationship between the acceleration, the net force, and the mass of a modified Atwoods machine. So, in other words, at the end of this lab cycle here, we should end up with one equation that has force, mass, and acceleration in it in some combination. And we'll see what that is as we go through the lab. And in fact, if you think about this, since we have 2 independent variables, we're going to have to do 2 separate labs, right? Because good lab technique, you only change 1 variable at a time. So when we change either the net force or the mass, we've got to leave the other one constant so that we're only changing 1 variable at a time. And I'll show you in the post lab then how we'll take these 2 labs and shove them together into one math model. So let's talk about the 2 parts of the lab. Okay. First of all, we can measure mass quite simply. There are electronic balances around the room. You can just put the card on it, and the masses have their mass written right on them. The black bar mass we're going to use, you can put on the balance, so those are fairly straightforward. Now, the acceleration, well, the force we know we can calculate already, mass times gravitational field strength. The acceleration, we're going to use Data Studio. You'll notice there's a motion detector on the back end of every track, and you know that with the motion detector we can make a graph of velocity versus time. So let me show you basically what your graphs should look like. This is a typical graph you're going to get. So let's talk about what's going on here. Okay? It's a graph of velocity in meters per second versus time in seconds. So here the velocity is 0. So this is before you've let the cart go. Right? You've hit start, but you haven't let the cart go yet. Here is where the velocity is changing. So here is where the cart is accelerating. Now eventually the masses are going to hit the ground. And when they hit the ground, right, the cart will stop to accelerate. And then you're going to catch the cart, and it will very quickly slow down and stop. Please make sure you catch the cart, otherwise it's going to hit the pulley and fly away and break, and they're expensive. So again, this is before you let it go. This is while it's accelerating. If you have this little part, this is where the masses have hit the ground, but it hasn't been stopped yet, and then this is where you catch it. Now, we want the acceleration, and hopefully you know that the slope of a velocity time graph is the acceleration. So if we choose the part of the graph by clicking and dragging over the graph, and we just want the linear part here, right? I want it after you let it go, but before you catch it. Right? So I want this part of the graph. And then down here, I've already turned on the linear fit, and here's your slope. This cart in this trial that I recorded was accelerating at 0.361 meters per second every second that went by. And it's really easy to get rid of this. You click, you get rid of that. You use Alt- to delete the trial, and you can run another trial. But only select the part you want, right? And then the slope of that after you select it is the acceleration. And by the way, you need to select every time. You can't just assume that it's going to have caught the right part the next trial. Okay, so every time you got to click and drag to select the part that you want. So that's actually a fairly accurate way of measuring the acceleration each trial, and a fairly quick way. Okay, now when you go to the website, and you'll have to go to Today on the website and open up the Newton's second law data sheet, as it's called. And when you do, the first thing it's going to tell you to do is to open the Data Studio file Newton's second law. That will open up the the file that you just saw. All right, so that you can measure the acceleration. And it is, of course, a link, and you just click on it, and it will open up the file for you. And by the way, we're going to have to do two parts of the lab. So this is the first half of the lab. This is acceleration versus force with constant mass. That means we're going to change the force, but leave the mass constant. Okay? Now, the second thing you're going to do, and again, this will be right on the screen that you'll be able to read, is you're going to put these masses in the cart. And in fact, they should already be sitting in the cart right now. One black bar mass, right, whose mass you're going to have to measure and then fill in the blank. One 10-gram mass, which is, of course, 0.010 kilograms. Two 20-gram masses, which is, of course, 40 grams, or 0.040 kilograms. One 50-gram mass, which is 0.050 kilograms. Three 100-gram masses, which is 0.300 kilograms. And one 200-gram mass, 0.200 kilograms. And once you figure out the mass of your black bar mass, there should be around 500 grams or 0.5 kilograms, but they might vary by a few grams here or there. So once you put yours in, you can add them all up, right? And that's the total mass that you have in the cart. Right? So all those masses go in the cart. Now, the question is, how are we going to do this part of the lab? Right? How are we going to change the force but keep the mass constant? Well, remember, we're using a modified Atwoods machine. And as we talked about a moment ago, the force is the force of gravity acting on B. So if we want to change the force of gravity acting on B, how can we do that? Well, we can do that by putting masses on B. Right? So if we put more mass on B, now it has a bigger force of gravity. That's a bigger force. But we want to keep the system mass constant. So we can't just grab masses from the table and put them on B, because now we've changed the force and we've changed the mass. But remember, there's a whole bunch of masses sitting on A. What if we took a mass from A and put it on B? Watch that again. We took one of the masses off of A and put it on B. Now, the total mass hasn't changed, but the amount of force, the force of gravity acting on B, has changed. So that's how we're going to manipulate this first half of the lab. Okay, and this is a key thing in order to get good data. To keep the mass constant, all mass must stay either on the string or in the cart. Okay, so you're going to start with all the masses in here, and you're going to move masses onto the end of the string. Now, you're going to start out by taking 40 grams, 0.040 kilograms, from the cart and adding it to the end of the string. And don't forget, the little plastic mass hanger you're using has a 5 gram, 0.005 kilogram mass. Okay, so you actually have 45 grams of mass on the end of the string. Okay, you'll see that on the data table you're filling in. But you need to be careful here that you actually do the 45, right, total. So you're moving 40 and there's 5 total. Right? By the way, these bullet points are on the data sheet so you can see them. And then you need to make sure the string stays parallel to the track, okay, horizontal, which it should unless the pulley gets moved around or something. But it needs to look like the picture, basically. Okay? Now, you'll see on your lab sheet that I want you to run 3 trials of each force. So every time you move some masses from the cart to the end of the string, you're going to run 3 trials and measure the acceleration 3 times and record them in the data table. And then you'll move different masses from the cart to the end of the string, each time changing the force, keeping the mass constant. When you're done with that part of the lab, you find your average accelerations, and then you graph acceleration versus force. Right? Acceleration will be the vertical axis, force will be the horizontal axis, because it's the independent variable, right, with constant mass. And then you'll call me over to look at your graph and make sure it's okay, and you'll record it and all that good stuff.